Welcome to Dr. Boxy Teaches Electromagnetism. In physics, we describe electric and magnetic phenomena using fields, E and B, the electric and the magnetic field. And if you look at the Maxwell equations next to me here, what you see is that the E and the B are not given directly themselves, but rather we are given their derivatives, their divergence and their curl. And so if we want to extract from those the electric and the magnetic field, to understand what the physics is of those phenomena, we need to be able to solve these equations to get the E and the B out of there. Now, to get rid of derivatives, what we need to do is to integrate. And so we will use the integrals that we introduced in the previous lesson today to see how to get rid of divergences and curls. So let us get started. We start with the case of gradients. So consider a scalar field Txyz, and remember that when we move around in space, the change in t is given by the following expression. The change in t dt is equal to the gradient of t dotted with the displacement dl. That is an expression that we saw in one of the previous lessons. Now we want to use this to see if we can get rid of gradients by integrating them out. So imagine we walk around in space following some trajectory, which I drew here. So this is the trajectory, the path P, going from a point A to a point B. And we will do what we did in one of the previous lessons when we defined integrals, which is we will subdivide the trajectory into smaller parts. So this here, I will call it L0, here is L1, L2, L3, etc., up to B, which will be Ln. And if we now look at the ith part of the trajectory, and this is Li minus 1, and this here is Li, and we define the vector going from Li minus 1 to Li, this vector, as dLi. So that's a tiny change in L, in the position along that line. And so for each of those parts, for the ith part, the dti, the change in the t in this ith part, is equal to the gradient of t in this ith part dotted with dli. And if we now want to find the total change in t, we have to sum all of these over the whole trajectory going from A to B. So that means I take the sum of both sides for I going from 1 to n. Now, as n goes to infinity, the parts become smaller and smaller, and the right-hand side, as n goes to infinity, the right-hand side becomes the line integral over this trajectory p of the gradient of t dot dl. While the left-hand side, all we're doing is we're summing the changes in t, so what we will get is the total change in t, which is t at the final point minus t at the initial point. And what we find here is a kind of fundamental theorem, but then for gradients, it tells us that integrating out a gradient of a scalar field amounts to getting rid of both the integral and the gradient, and all we're left with is the actual scalar field, but then evaluated at the endpoints of that path and subtracting them from each other. So this here is the fundamental theorem, but then applied to gradients. So let's see a couple of consequences of this. The fundamental theorem tells us that if we take a path from A to B, that the line integral of the gradient is equal to the scalar field evaluated at the endpoints and then subtracting them from each other. So one consequence, one corollary of this, is that the line integral of the gradient of a scalar field is independent of which path we take from A to B. It only depends on A and B themselves. So if we follow the path from A to B, which I drew here, or if I take a different path, for instance, this one, in both cases, the line integral of the gradient along either one of those paths will be equal to tb minus ta. In other words, it will be the same. So the line integral in general of a vector field does depend on the path taken, But if that vector field is the gradient of some scalar field, it does not. So that is one consequence. A second consequence is that the closed line integral, so the line integral along any closed path, will always be 0. And this follows again directly from the theorem itself. If we take some path which is closed, meaning that its starting point A and its end point B are the same, well, the right-hand side of the theorem tells us that the line integral along this closed curve is tb minus ta, but as b and a are the same point, tb minus ta is 0. So we indeed find that the closed line integral of the gradient of a scalar field t is always 0. So let's see if we can see this theorem at work in some example. We consider the scalar field t given by xy squared and 2 points a and b, where a is the origin and b is the point 2, 1, 0. And we want to check the fundamental theorem using two different paths going from a to b. So we're going to calculate the left-hand side of the theorem, so the line integral on the one hand, and on the other hand tb minus ta, and check that we indeed get the same results. And additionally, that those results do not depend whether we go from a to b using path 1, the red one, or path 2, the green one. So first of all, we need for the left-hand side to be able to calculate the gradient of t. And so what is it? The gradient of t is a vector with an x component and a y component. There is no z component because there is no z dependence in t. And the x component is the partial derivative of t with respect to x, which is y squared. And the y component is the partial derivative of t with respect to y, which is 2xy. So this is the expression for the gradient of t. And we now want to calculate the line integral, so the left-hand side, along path 1, which is the line integral along this path. And so we would divide path 1 into two parts. In the first part, the horizontal part, we have that dl is only moving in the x direction, so it's of the form dx x hat. And therefore, the gradient of t dotted with dl is equal to y squared dx. But y is constantly 0 along this first part of the path, and therefore this dot product is 0. And thus the line integral along part 1 here of the gradient of t is 0. If we now look at part 2 of this path, well, along this part 2, dl is vertically upward, so of the form dy y hat. And therefore, the dot product of the gradient of t with dl is 2xy dy, where x now has a constant value of 2 because the x component of b is 2. So that means it's 4y dy. And so the line integral along part 2 of path 1 of the gradient of t dl is equal to the integral of 4y dy, where y goes from 0 to 1. The integral of 4y dy is 2y squared, and we need to evaluate this between 0 and 1, which gives us 2. And so to sum up, the full line integral along path 1 of the gradient of t dl is the sum of the two results we just found, which is 0 plus 2. In other words, we simply find 2. So this is the result for the left-hand side if we take it along path 1. If we now look at path 2, along path 2 is given by the equation y equals 1/2 x, and therefore along this path, the change in y is always equal to half the change in x. And so we can write dl along this path as, in general, it would be dx x hat plus dy y hat. The dx x hat, I leave it, and the dy, I replace it by 1/2 dx, so we get plus 1/2 dx y hat. And so the dot product of the gradient of t with dl is equal to y squared dx plus 2xy times 1/2 dx. We can get rid of the 2 and the 1/2 in the second term, and we can now replace all the y's by 1/2 dx, sorry, by 1/2 x, and so we get 1/4 x dx plus 1/2 x squared dx, which gives us 3/4 x squared dx. And therefore the line integral along path 2 of the gradient of t is the integral of 3/4 x squared dx, where x ranges from 0 to 2. Now the integral of 3/4 x squared dx is x cubed divided by 4, and that needs to be evaluated between 0 and 2, which gives us 8/4, which is indeed 2. So we find the same value of 2 when we evaluate the line integral, so the left-hand side along path 2. And now we want to check the right-hand side, and the right-hand side is actually the easiest part. All we need to do is to evaluate t, the original scalar field at the points A and B. Now, in point A, it's the value of xy squared, where both x and y are 0, so t of A is simply 0. T of B is xy squared, where x is equal to 2 and y is equal to 1, and that gives us 2, and their difference is indeed 2. tb minus ta is indeed 2. And so at least for this scalar field and following these two paths, we find that the fundamental theorem holds, and it holds indeed in general. For divergences, we start with a vector field V and some three-dimensional shape. Its volume, I will represent it by the capital letter V, and its surface, the boundary of that volume, will be represented by S. Now, the theorem for divergences, the fundamental theorem, looks like this. What do we have here? On the left-hand side, we have a volume integral of the divergence of V. On the right-hand side, we have a surface integral of V itself. Notice what happened here. Going from left to right, we got rid of the divergence, so we got rid of a derivative. But we at the same time also got rid of one of the integrals, because on the left-hand side we have a triple integral, it's a volume integral, while on the right-hand side we have a double integral, a surface integral. This theorem is known as Green's theorem, and just like with many other theorems in this course from mathematics, I will leave the proof itself for a course in mathematics which will be given in the future. But at least from an intuitive point of view, this gives us an idea of why we think of the divergence as the amount of field leaving a certain point in space. Why is it? Well, on the right-hand side, the surface integral, so it's an integral over the boundary of that volume V, well, the right-hand side is the flux out of that boundary. So on the right-hand side, we have the surface integral of V, which actually tells us how much of the field V leaves the boundary. On the left-hand side, we have a sum, an integral, of the divergence of the field throughout that volume. So if we think of that divergence as the amount of field leaving a point, this theorem makes some intuitive sense. And that is why we use that idea in mind when we think of the divergence of a field. So this is the theorem for divergences. Let us now go and look at at the case of curls. For the case of curls, we start with, again, a vector field V, and this time we take a path P, which I drew 3 times here. Now, any path, any closed line can be thought of the boundary of some surface, but it can actually be thought of the boundary of an infinite number of surfaces. One possible surface that has this path P as its boundary is this one. So in this case, think of it as an igloo where the surface is the actual igloo itself, while the path is the line where the igloo sits on the ground. And so the path P is the boundary of this surface S, but that same path P is the boundary of, for instance, this surface, or of the flat surface given here. In all these cases, the path P is the boundary of those surfaces. Now, what does the fundamental theorem for curls tell us? Well, it says that if we take the surface integral of the curl on any of those surfaces, the result would give us the line integral of V itself. So notice again that going from left to right, we actually got rid of the curl, so we got rid of a derivative, but we again also got rid of one of the integrals, because on the left-hand side we have a double integral, a surface integral, while on the right-hand side we have a line integral, a single integral. This theorem is known as Stokes' theorem. And we will see in what sense we can think of this as a way to understand the intuition that I spoke about in one of the previous lessons, namely that the curl can be thought of as the amount of rotation there is within a field. So let us look at that. We start again with the line, the same line which I drew twice here. And the fundamental theorem tells us that the curl of the vector field over the surface is equal to the line integral of the field itself over the boundary of that surface. So think again of the boundary of the surface as the line, and the surface I will take it to be flat this time. And we will look at the left-hand side and the right-hand side of the theorem separately. So on the left-hand side, imagine I put a grid on that shape. So on that surface, I will put some grid on there. And so we get something that looks like this. And if we now zoom in on two of those rectangles, so let's say this is one of them, and this is another one. If we indeed think of the curl as being related to the amount of rotation there is, well, in that case, the curl in the bottom rectangle will be related to how much rotation there is within that rectangle of the vector field. Now, if we do the same thing for the upper rectangle, we get this. And notice what happens now if we add those two curls. What happens is that the curl on the common boundary, so the one on the top boundary of the bottom rectangle or at the bottom boundary of the top rectangle, they cancel each other out. So when we add all of these curls over the rectangles, what we will be left with is the amount of rotation there is only on the outside. So if we think of the curl as indeed relating to the amount of rotation there is, what the theorem tells us is that adding the amount of rotation there is within the whole surface amounts to only looking at how much the field is rotating on the outside of that shape. And that is exactly what the right-hand side tells us. The right-hand side says, look at V and add the amount of V there is that moves with our motion along that line. So that is exactly the line integral of V. And so in that sense, we can think of the theorem as telling us that the curl of V is indeed related to the amount of rotation there is in the field. Now I do have to mention that there is some freedom here. You need to make a choice. For the right-hand side of the theorem, there is a line integral, but we need to choose whether we follow that line in clockwise or in counterclockwise direction. While on the left-hand side, you have a surface integral, but it is an open surface. And we said when we introduced surface integrals that there is no convention on in what direction we choose A. It had to be perpendicular to that surface, but it could be in this case either towards us out of the screen or away from us into the screen. And the convention is the following. We need to use a right-hand rule that makes sure that whatever choice we make, it needs to be consistent on both sides of the equality. So in this specific case, for the right-hand side, I chose to follow the path, the line, in counterclockwise direction. In that case, what you need to do is take your right hand and close your fingers in counterclockwise direction. What you see is that in that case, the thumb points towards you. And so in this case, the dA integral, the surface integral, must be chosen such that dA points towards us. If we were to choose dA in the opposite direction, away from us, then you need to point your thumb of the right hand away from you. And if you close your fingers in that case, you will see that they close in clockwise direction. So if we choose dA away from us, which is allowed, you can choose it that way, but in that case you have to choose the line integral taken clockwise. So you can make whatever choice you want, you just need to be consistent in it. Let us look now at a couple of consequences of the theorem. The theorem says that the surface integral of the curl of a field is equal to the line integral of the field itself, where the line integral is taken over the boundary and the surface integral over the actual surface itself. So one consequence of this theorem is that the surface integral of a curl of a field does not depend on what surface we choose, but only on the boundary line. So remember 2 slides ago we looked at differently shaped igloos. What this says is that it doesn't matter exactly what the shape of the igloo is, as long as the boundary line is the same for all the igloos, the surface integral of the curl will be the same. So in general, it's not true that the surface integral of 2 fields with the same boundary line will be the same, but it is true when that field is the curl of some other field. A second consequence, a second corollary, is that if we take the surface integral of the curl but for a closed surface, what we will get is always 0. And the idea here is that the theorem tells us that the surface integral of the curl is equal to the line integral of the field itself over the boundary, but for a closed surface there is no boundary. We can think of the boundary as being a line of length 0. And so in that sense, that right-hand side tells us that it should be 0. So for a curl, the surface integral of the curl of a field will always be 0 when taken over a closed surface. So let us now look at how this theorem works with an example. So we consider this vector field and we want to check the theorem for this shape. So for the line integral, we will take the rectangle with side 1 on the YZ plane, while the surface integral will be taken as the flat surface within that rectangle. So we again will calculate the left-hand side and the right-hand side separately. Now, first of all, we need to calculate the curl of V. So remember that the curl of a vector field can be calculated using a determinant. Specifically, we have the first row will be the unit vectors x, y, x hat, z, y hat, z hat. The second row are the components of the del operator, which are the ddx, ddy, and ddz. And the third row are the components of v, vx, vy, vz. So what do we get? We get x hat multiplied with the y derivative of the z component of v, which is 4z squared, minus the z derivative of the y component, which is 2x, plus y hat. That is multiplied first with the z derivative of vx, which is 0 because there is no vx, minus the x derivative of vz, but vz doesn't have an x in it, so it's also 0. In other words, the curl will not have a y component, plus z hat multiplied with the x derivative of vy, which is 2z, minus the y derivative of vx, which again is 0. And so what we find is that the curl of v is equal to 4z squared minus 2x times x hat plus 2z z hat. And notice that x all along this curve and all along this surface has a value of 0. In other words, the x can be plugged in, we can plug in 0 for x, and we're left with the curl of v equal to 4z squared times x hat plus 2z times z hat. And we now want to calculate the surface integral of this curl. So here is the curl. And what is the surface integral? What is the surface we're considering? Well, dA, because we took we take the line, which we will do on next slide. For the line integral, we take it in counterclockwise direction. we close our fingers of our right hand in counterclockwise direction, and we see that our thumb points towards us, in other words, in the positive x direction. And that means that dA is equal to dy dz times x hat, and therefore the curl of v dotted with dA is equal to 4z squared dy dz. And so the surface integral itself of the curl of v is the double integral over y and z, both of them going from 0 to 1, of 4z squared. Now the 4 can be taken out of the integral, and the y integral can be solved immediately because there is no y dependence in the integrand, so that just gives us 1, multiplied with the integral of z squared dz, which is z cubed divided by 3, and that needs to be evaluated between 0 and 1, which finally gives us 4/3. So the left-hand side of the theorem, so the surface integral of the curl, gives us 4/3. Let us now look at the right-hand side. So for the right-hand side, we need to take the line integral. The line is following the square in counterclockwise direction. And I will calculate the line integral for each of those 4 sides. For side number 1, dl is only moving in the y direction, so it's dy y hat, and therefore v dot dl is equal to 2xz plus 3y squared dy, where again x has a value of 0, so that's simply 3y squared dy, and this needs to be integrated, so the integral along part 1 of the line is the integral of 3y squared dy, where y goes from 0 to 1, which is the integral of 3y squared dy is y cubed. This needs to be evaluated between 0 and 1, which gives us 1. So this is the value of the line integral along part 1. For part 2, dl is in this case equal, it's only a motion in the z direction, so it's dz times z hat, and therefore the dot product of v with dl is equal to 4y z squared dz. And notice that along this path, y has a constant value of 1, so we're left with 4z squared dz. And so the line integral along part 2 here is equal to the integral of 4z squared dz, where z ranges from 0 to 1. The integral of 4z squared is 4z cubed divided by 3, and all of this evaluated between 0 and 1, which gives us 4/3. For part 3, dl is, the motion is only in the y direction. Now it is in the negative y direction, so you may want to write this as minus dy y hat. But notice that dy is a change in y. And so if we integrate this with y going from 1 to 0, dy itself is already negative. So if we were to add an additional minus sign here, we would actually make it positive, which is not what we want to do. Y is decreasing. So dy is not necessarily a positive quantity. Dy can be positive or negative depending on the boundaries of the integral. So in general, what I will do when I write dl is I will write dl as dx x hat plus dy y hat plus dz z hat, and I will make the boundaries of the integral take care of the sign of the dx, dy, or dz that we're considering. So in this case, dl is dy y hat, and therefore v dot dl is 2xz plus 3y squared dy, where once again we can just plug in 0 for x and we're left with 3y squared dy. So the integral along part 3 of the curve is the integral of 3y squared dy. But this time y ranges not from 0 to 1 but from 1 to 0. The integral of 3y squared dy is y cubed. And this needs to be evaluated between 1 and 0, which gives us -1, -1. And finally, for part 4, dl is in this case dz z hat, and once again I don't put a minus sign here, the boundaries will take care of that. V dot dl is equal to 4yz squared dz, which is 0 because y is 0 along this part. And so the line integral along part 4 is 0. And to summarize, what we find is that the total closed line integral over the full path is equal to the sum of the 4 integrals we just calculated. The first one was 1, the second one was 4/3, the third one was -1, and the fourth was 0. And so we're left with a total of 4/3, which is the exact result we found for the left-hand side of the fundamental theorem. So this is a check again for this specific vector field and for this specific shape that the theorem holds, and it holds indeed more generally. To summarize what we did now, look again at the fundamental theorem of calculus for functions of one single variable. It tells us that we can get rid of a derivative if we at the same time get rid of an integral. And what we're left with is the value of the function evaluated at the boundaries of that interval and then subtracted from each other. Well, what we saw are 3 versions of this theorem, or rather 3 generalizations of it. Firstly, when we take the gradient of a scalar field and we move around in space from a point A to a point B along some path P, the line integral of the gradient, we can get rid both of the derivative of the gradient and of the integral, and we're left with the scalar field itself evaluated at boundaries A and B and then subtracted from each other. For divergences, we saw that the volume integral of the divergence is the surface integral over the boundary. So here have a 3-dimensional shape in mind, so something which looks maybe a little like this. So think of this as some 3-dimensional shape. And in this case, what we're doing is we're integrating the divergence of a vector field V over the full volume of that shape. And what we're left with is we got rid of the divergence of the derivative and of one of the integrals, and we're left with a double integral over the surface, the boundary of that shape, which gives us the closed surface integral of V. Again, notice that what we have is, again, we evaluate what we get, but on the boundary of it. Just the boundary for a line are the 2 endpoints. The boundary for a volume is the surface. And finally, for the curl, we have that the surface integral of a curl, so think again of some shape, which is the boundary of a surface. Take, for instance, this surface. And once again, the surface integral of the curl is equal to the line integral of the field itself, where once again, the boundary of the surface we evaluate, we get rid of the derivative of the curl and we get rid of one of the integrals, and we evaluate the function on the boundary, and in this case the boundary of a surface is the line around it. So these are all versions of the fundamental theorem of calculus that we will need in this course. In the next lesson, we will look at how to work with many different kinds of coordinate systems. It will turn out to be necessary to not only work with Cartesian coordinates, but with other coordinate systems, and we will look at that in the next lesson. See you then.